So you want to know the secret to be a millionaire by knowing the future? Well, this video is for you. The secret is
Finally. Oh, yes. The power of the Dragon Scroll is mine! It's nothing!
It's okay. I didn't get it the first time either.
What?
There is no secret ingredient.
predicting the future with absolute certainty is impossible. But wait, we can certainly make predictions about the future with reasonable accuracy. Humans predict the future as a fundamental aspect of their survival instinct. The ability to anticipate future events and outcomes has been crucial to human survival and evolution. It allows individuals and communities to make informed decisions, plan for the future, adapt to changing circumstances, and ultimately enhance their chances of survival and well being in an ever changing world. In this video series, we'll be focusing on time series analysis. In simple terms, time series analysis helps us understand and make predictions about things that change over time. Time series analysis is the backbone for prediction and forecasting analysis, specific to time based problem statements. Let us understand this through an example. Consider a farmer who wants to sow seeds in his farm. He wants to get the maximum output from the sown seeds. That is, he wants maximum seeds to germinate. So, when should he sow the seeds? You know that water is important for germination of seeds. So, ideally, one should sow the seeds just before the monsoon season to get the best results. So, now we want to know when the monsoon season will start. According to the climate of the region, the monsoon season starts in June, so it would be best to sow the seeds sometime in late May. What we have done in this example is time series analysis. We analyzed time varying data, which in this case were the weather patterns, to predict when the monsoon season will start. Based on the prediction, we made reasonable decisions to best suit our outcome. Time series analysis has evolved over time with advancements in mathematics, statistics, and computing. Let us look at some of the methods used for the analysis of time series data. First is plotting of time series data. One of the earliest and simplest ways to begin analyzing time series data is by plotting it. Visual inspection can reveal patterns, trends, and seasonality. Early on, hand-drawn graphs and charts were used for the purpose of plotting time series data. Consider this example. By plotting the data of different European stock exchanges and observing the trends, we can conclude that data from different European stock exchanges is highly correlated. Next is the method of least squares. The method of least squares was first introduced by Carl Friedrich Gauss in 1805. It is a statistical approach for fitting linear models to data, including time series data. The method works by minimizing the sum of the offsets or residuals of the points from the plotted curve. The following animation describes the working of the least squares method. The line corresponding to the minimum of the residual sum of squares is the best fit line for the least squares method. Next is autoregression. Autoregression measures the linear relationship between the lagged values of a time series. The concept of autoregression and the correlation function were developed in the early 20th century and remain fundamental to time series analysis. In the following example, the sample time series data of temperature recorded in a city is shown in the blue graph. An autoregressive model is trained on a training set of this data and predictions are made, denoted by the green graph. Next is the moving average model. One of the early techniques for analyzing time series data is the moving average model. Rather than using past values of the forecast variable, like in autoregression, a moving average model uses past forecast errors in a regression-like model. The following simulation represents the moving average model. The moving average model is trained on historical data and the predictions, represented by the orange graph, are compared with the observed data, represented by the black graph. We will take a deeper look at the moving average model in upcoming videos. Next is exponential smoothing. The exponential smoothing method was developed by Robert Brown in the 1950s. It is a technique for making forecasts based on past observations and assigning exponentially decreasing weights to older data points. The more recent data points are given greater weights than the ones further in the past. The following simulation explains the exponential smoothing method. The blue graph represents the exponentially decreasing weights given to the lagged values. The predicted values are represented by the red graph and the original data is represented by the black graph. Next is the Box-Jenkins methodology. The Box-Jenkins methodology, which was introduced by George Box and Gwilym Jenkins, laid the foundation for modern time series analysis. This methodology involves a systematic approach to model identification, estimation, and diagnostic checking. It is also known for its development of autoregressive integrated moving average or ARIMA models. ARIMA combines autoregressive features with those of moving averages. An ARN process is the one in which the current value is based on the previous n values. As a result of this combination of techniques, ARIMA model can take into account trends, cycles, and other non-static type of data when making forecasts. This simulation shows the working of the ARIMA model. The ARIMA model is trained with the past values of the data. If we try to predict the value at the nth time step, the ARIMA model recursively predicts the values of all the time steps between the current time and the nth time step and then calculates the value at the nth time step. Now let us discuss the pros and cons of using ARIMA models. The pros include, firstly, that it is good for short-term forecasting. Secondly, it only needs historical data and no other data is required for ARIMA models. Lastly, ARIMA can also model non-stationary data, something that the moving averages model and the autoregressive model cannot do. The cons include that it is not built for long-term forecasting. Secondly, ARIMA models are poor at predicting turning points. ARIMA model is also computationally expensive. Lastly, the parameters of ARIMA model are subjective. Further in this video series, we will try to take a deeper look at the Box-Jenkins method and the ARIMA model. In the next video, we will take a look at the stationarity of data, which is important in time series analysis.